Welcome back. We are going to now talk about angular acceleration. So remember last time we had two types of motion. Translational was the linear kind where things move in a straight line, and rotational motion is also called angular motion, and that's where things rotate around an axis. So we've talked about angular displacement and velocity. Now we're going to pick up angular acceleration. Its variable is the letter alpha, so it's that Greek lowercase alpha. You might have it drawn more like the fishy or the ichthus if you studied theology, but it's the lowercase Greek a. And since acceleration typically is defined as the rate of change in velocity, angular acceleration will now be the rate of change of angular velocity. So we're just going to add in that word to let us know we're rotating. So last semester when we talked about acceleration, it was change in velocity over time. Now our angular acceleration is change in angular velocity over time. So this is our rotational version. And if you haven't noticed, angular and rotational will be used interchangeably with each other. And to relate the translational or linear acceleration with this rotating or angular kind, we can put those together in this formula. So our regular acceleration, which is the a, would be equal to the radius of the circle that you're rotating about times the angular acceleration. Remember from last semester, regular acceleration was meters per second squared. Radius should still be in meters, and now our angular acceleration is radians per second squared. This slide has a very nice summary for combining our types of motions. So just to walk you through, the quantity that we are going to be comparing will be displacement, velocity, and acceleration. These two columns are the linear ones. This is what we've had before. Displacement was a d in meters, velocity was a v in meters per second, and acceleration was an a with meters per second squared. We did not have an equation for displacement, we just simply made a measurement. When we did velocity, it was displacement over time, and acceleration was velocity over time. You can also put in your deltas in front of the displacement and in front of the velocities to remind you that it's a change as well. Next, these two columns are the angular or rotational equivalent. So before, where we had displacement as a d in meters, now the rotational or angular version will be a theta in radians. Again, no equation, it's just a measurement. Next, we have velocity. It was a v and change in displacement over time. Now it's going to be an omega. Instead of meters per second, it's radians per second. And change in displacement over time is now change in angular displacement over time. Lastly, we have acceleration. Instead of an a, we have an alpha. It's the Greek a. Instead of meters per second squared, we have radians per second squared. And then for our formula, linearly, we had acceleration as the change in velocity over time. Now rotationally or angularly, we have angular velocity over time. And now our last column shows us how the linear and the angular are related to each other so that both of them are in the same formula. As you can see, to get from linear to angular, we simply multiply the angular version of our quantity by the radius every time, and that would give us the linear version that we're used to. For Roman numeral 2, now we're going to take this rotational motion and apply it to kinematics. Hopefully you remember kinematics from last semester. You can always go back and look at your notes if you need to. But we are going to compare what we've already learned and now apply it to rotational motion. So noting that the direct relationship between translational and rotational quantities, what we're going to do is rewrite each of the kinematic equations from last semester and turn it into a rotational kinematic equation. Last semester, our first kinematic equation was final speed equals initial speed plus AT. All we're doing is replacing those variables with their rotational counterpart. So instead of a v, we have an omega. So now it's angular speed or angular velocity instead of regular velocity. And then we have our angular acceleration instead of linear acceleration. And then time stays the same. So let's do this with the other two kinematic equations. The second kinematic equation was distance is VIT, initial speed times time, plus 1/2 AT squared, 1/2 acceleration times time squared. So we make substitutions and we now have theta, which is our angular displacement. That's equal to omega t, which is angular velocity times time, plus 1/2 alpha t squared, 1/2 the angular acceleration times the time squared. And finally, our last equation, VF squared equals VI squared plus 2AD. The V's get replaced with omegas, so now they are angular velocities. The A gets replaced with an alpha, so it's angular acceleration. And the D gets replaced with theta, it's angular displacement. All of these equations work and behave in the same way as what we did before. They just have new letters to let us know that an object is rotating instead of moving in a straight line. So let's try an example problem together. We have a turntable, which is an old record player, capable of angularly accelerating at 12 radians per second squared. So let's write that one down. Angularly accelerating would be our alpha, and that's 12 radians per second squared. It needs to be given an initial angular velocity if it's to rotate through 400 radians in 6 seconds. So 400 radians will be our angular displacement. And then obviously 6 seconds is going to be our time. And we are asked to find this initial angular velocity. So that would be the omega, the curvy W, initially. So go back and look at your kinematic equations and see if we should use the first, second, or third one. I hope you saw that there was no final angular velocity, so that leaves us with the second kinematic equation. I'm going to go ahead and rearrange this first. If you prefer, you can plug your numbers in, but I'm going to rearrange the formula and then plug my numbers in. Since I'm interested in finding the initial angular velocity, I take this term that does not have that variable in it and I subtracted it over to the other side. And that leaves us with this row. Now I can see that I simply need to divide both sides by the time. So let's plug our numbers in and solve. Since this is a little bit longer formula, I'm going to go ahead and write out some steps for you, so we're still going to continue. And I would say that the initial angular velocity would be 400, and I'm going to type this part out in my calculator and come up with 216, and then we still need to divide the whole thing by 6. So if I subtract my 400 minus the 216, that's going to give me 184 on the top and 6 seconds still on the bottom. Now I simply divide those and I get an initial angular velocity of 30.7. The units will be radians per second. That's it for now. Your next quest assignment is going to have quite a bit of problems with the angular version of kinematics and comparing the linear and the angular formulas that we've had already. So I'm going to try to give you some more class time than usual so that we can work on those together so that you can get a good feel for how to move from linear to rotational. Good luck.